Okay, let's just dive right into this explainer. Welcome to what I like to call a cognitive masterclass, and it's designed specifically to rewire your brain. Today, we're not just going to sit here going over boring code syntax. Instead, we're going to train your mind to instantly recognize and solve queue-based algorithm problems, literally exactly like an ex-Google interviewer or a competitive programming coach would. So if you've ever find yourself totally stuck, wondering exactly when you should use a breadth-first search or maybe a sliding window, well, you are absolutely in the right place.
Real quick, here's our roadmap. We'll kick things off with the intuition behind the FIFO principle. Next, we'll master BFS layer by layer. Then we dive into the really fun stuff, Deques and sliding windows, before finally wrapping up with pattern recognition and some common pitfalls to avoid. Let's get to it.
Starting with Section 1, Intuition and the FIFO Principle.
To really build out your mental map, let's start with a super basic question. What specific type of chaos were queues actually designed to fix? Well, queues exist to enforce perfect fairness. They ensure first in, first out, or FIFO processing. This completely solves problems where the order of arrival just has to be strictly preserved. Whenever you ask yourself, do these items need processing in the exact order they showed up, you are looking at a queue. Think about everyday real-world stuff. A ticket counter, an ATM line, or that miserable airport security checkpoint. The person who gets there first gets served first, period.
And that brings us to the brilliantly simple distinction between the two most common linear data structures. While a stack actually defers processing to handle the newest items first, like hitting the undo button on your keyboard or resolving nested brackets, a queue maintains that perfect fairness. By resolving the earliest items first, the queue naturally becomes the absolute engine of layer-by-layer exploration.
Which leads us straight to Section 2, BFS and layer-by-layer mastering.
This is where the magic of the queue really shines. Breadth-first search. Imagine a tree structure. A queue literally forces us to explore nodes layer by layer. BFS demands that we start right at the root, and we absolutely must visit all of its immediate neighbors before we are allowed to go even one level deeper. It creates this perfectly uniform, radiating expansion. To pull off that uniform expansion, we rely on a four-step process. Think of this as the unbreakable BFS heartbeat. Step 1, initialize your queue with the root. Step 2, pop a node from the front. Step 3, process that node. And Step 4, push all of its unvisited neighbors to the back of the queue. Then you just repeat. This strict FIFO behavior guarantees we will always find the absolute shortest path in any unweighted structure.
But here's the crucial point. You have to know your environment. In a tree BFS, the structure is naturally safe, right? There are no cycles, so you don't even need a visited set. It's literally impossible to loop infinitely. But in a graph BFS, connections can loop right back on themselves. You absolutely must track your nodes with a visited set to prevent catastrophic infinite loops. It's a total game changer.
Moving on to Section 3, Deques and sliding windows.
Okay, we are ready to escalate to some advanced mechanics. Standard queues only let you add to the back and remove from the front, while a Deques, or double-ended queue, completely shatters that limitation by allowing O1 constant time insertions and removals at both ends. And by giving us that front and back access, the Deques becomes the ultimate tool for complex range queries, specifically for tracking the running minimum or maximum inside a sliding window.
Let's mentally dry run this so you can really see the cognitive model in action. Imagine an array and a sliding window of size 4. Think about how the Deques state manages these elements. To track the minimum, our Deques strictly maintains an increasing order. The front of the Deques, which in this first window happens to be the number 1, is always the absolute minimum of our current window.
Now, watch what happens when the window slides just one step to the right, introducing the number 3. The decree aggressively pops the 4 and the 5 from the back. Why? Well, because 4 and 5 are larger, and they're older. They can literally never be the minimum again, compared to the smaller, newer 3 that just arrived. We've instantly optimized away useless data.
As the window shifts again, our previous minimum, the 1, falls completely out of the window's range. Because it's now out of bounds, it gets cleanly popped right off the front. And this reveals exactly why we need that double-ended access. We remove outdated minimums from the front, and we crush obsolete larger numbers from the back, all while effortlessly maintaining O of n linear time.
Almost done. Section 4, Pattern recognition and pitfalls.
Finally, I want to equip you with some actual interview cheat codes. You see, understanding the data structure is only half the battle.
The other half is instantly identifying these exact patterns when you're under pressure. You need to train your brain's recognition triggers. The moment your interviewer says shortest path in an unweighted graph or minimum moves to reach a target, your brain has to instantly fire up the BFS and Q mental models. And if they mention a subarray of size K, boom, you immediately set up a fixed sliding window.
But you have got to avoid these common traps at all costs. In a graph BS, the absolute most fatal error you can make is marking a node as visited after popping it, instead of right when you enqueue it. That leads directly to redundant work and, yeah, those infinite loops. And in Ds, a massive mistake is storing the actual values instead of their indices. If you don't store the indices, you completely lose your ability to track when an element falls out of your sliding window.
So, I want you to train yourself to ask this diagnostic question every single time you read a new problem description. Do things need processing in arrival order? Or are we exploring layer by layer? Seriously, is this a FIFO scenario? Are we radiating outward step by step? If the answer is yes, grab your cue.
And please remember, mastering cues is absolutely not just a party trick for algorithmic interviews. It's the exact same logic used to build massive, distributed systems out in the real world. The principles you apply to a LeetCode problem are the identical principles powering message queues like RabbitMQ, event streaming platforms like Kafka, and even background job processing in operating systems.
I want to leave you with this final thought. The queue is the engine of perfect fairness. Think about your own work right now. What complex, chaotic problem in your current codebase could be elegantly solved by simply stepping back and enforcing a strict first-in, first-out rule? Just think about it, and let that question guide your next system design. Thanks for joining me for this explainer. Keep building those mental models, and I will catch you in the next one.